You're very welcome to the Soil Fertility Conference. This is the part three of a three-part series in this in this conference. We've had quite a lot of information so far, but first I'd just like to welcome our speakers for today. We've Mark Plunkett, we've Thomas McCarthy, Dr. Veronica Nyhan, and Dr. Dominaka Krol. So you're all very welcome, and looking forward to your presentations in a few minutes. I suppose to date in this conference, we've heard a lot around the efficiency targets that we're trying to achieve, and we've heard a good bit about the fertilizer register, around the fertilizer limits, trying to, I suppose, calculate your own fertilizer limits and to make sure that you kind of stay under those limits. We've heard a good bit around trying to minimize the environmental impact from nitrogen, I suppose, especially, and also the contribution that clover can make into the systems. Today, however, we're going to talk a little bit more around the P's and K's element of it, in terms of trying to maximize efficiency of both the P's and K's and production as well. We'll see where the use of organic manures kind of comes into that as well. And also then in terms of those slurries, in terms of organic manures, where additives can make a difference in those from the point of view of the environment as well. So for the moment, we'll keep going, and I'm going to ask Mark Plunkett maybe to present your slides, Mark, and we're going to hear a bit about P and K for the next 20 minutes. Mark, you put yours up.
Okay, good morning, everybody. Delighted to be here this morning to talk to you around the whole area of P's and K's. The title of my presentation here this morning is managing lime PK for productivity and reduced farm emissions. So again, just to give you an outline of my presentation, I'll give you a short introduction. I'll refer to the latest site test results, the latest fertilizer use. I'll also talk about lime. I'll also dig into a little bit around the whole area of P and K and its role in terms of end use efficiency. I look at the advice, the timings, and I'll finish up around, again, what are the most sustainable fertilizers that we should be considering in 2024 in terms of fertilizing our crops. So, okay, I suppose, look, the challenges, again, there's many challenges out there on the agricultural scene on the front. Again, climate change is a big one, I suppose. Just to remind people here this morning, we have a target of a 25% reduction in carbon emissions by 2030. We're getting quite close to that target as we speak in 2024. Also, fertilizer use, we've seen a significant reduction in nitrogen usage, and we're actually meeting our climate target of a 25% reduction. And also, I look at the whole topic of P and K formulation and how can it contribute in terms of meeting our climate targets. And look, very much on the agenda as we speak is the whole area of water quality. And look, if we get the above two right, it very much feeds into improving water quality. Okay, so maybe I'll pull you back a little bit here, and maybe just let's go back to the MAC, or the marginal abatement cost curve. And again, there's a number of, I suppose, technologies that are proven in there in our MAC. This is our roadmap in terms of reducing carbon emissions. But the things look that, you know, in terms of liming, digestate, clover multi-species, reduced crude protein, fertilizer formulation, low emission slurry spreading, and the improvement in soil P for fertility. So basically, all these measures, what they do is that they either replace nitrogen or improve the efficiency of nitrogen on farm. And that, I suppose, gives us confidence to maintain that 300,000 tons of chemical nitrogen, which we have achieved in, I suppose, on average in the last two fertilizer seasons. So again, if we pull all those technologies, again, if we look at them as building blocks, and you ask the question, what underlines, you know, what drives all above the line? And I'll tell you here this morning, it's soil fertility. So again, we are immersed in soil farming, agriculture. It's all about soil. You know, it's our resource, it's our productive medium. But getting the basics right in terms of pH, P and K will drive everything that's above the line, whether it's low emission slurry spreading in terms of reducing chemical nitrogen, whether it's fertilizer type in terms of switching our fertilizer formulation, clover multi-species. Again, a key, I suppose, cornerstone that Thomas McCarthy will tell us more about here this morning is that clover and multi-species have a major role in reducing chemical nitrogen usage on farm. But to get those, I suppose, those seeds into the system and established and to maintain their productivity, soil fertility underpins or underlines it very much so. Again, look, it has been referred to, I think, on all the conferences here to date and the previous two. But again, just to look at nitrogen usage figures over the last number of years, 2018 is our base, 408,000 tonnes. And again, our target is 300,000 tonnes. And in the last, I suppose, 2 years during the fertilizer crisis, look, farmers have, basically we have achieved our target. We have become, I suppose, wiser or cleverer in the use of chemical nitrogen in terms of, I suppose, feeding or maintaining our production systems. And if you average those two figures for 22 and 23, we're at about 310,000 tonnes, and our target is 300,000 tonnes. So again, I suppose that's one of the big challenges, and I suppose that's what I will address here this morning. How do we maintain that 300,000 tonnes in terms of reducing chemical nitrogen usage on farm? Also, look, another little bit around the targets. So again, we're very much on the drive, and we're being successful, and farmers have been very successful in the use of NBPT treated urea. And again, it's a sustainable, a low-cost form of fertilizer. Again, we are moving away from the traditional pasture and cut sward type fertilizers, our 27s or 24s. Look, in practice, they tend to be a dear way of buying P's and K's, and again, they're not good for climate. It's the form of nitrogen that has dominated those products. It's a nitrate-based nitrogen, and again, it's not good in terms of reducing our carbon footprint or reducing nitrous oxide emissions. And again, we're very much moving to the more traditional type fertilizers in terms of your 18-6-12s, your 10-10-20s, 13-6-20s. And again, these tend to be the best way of buying P's and K's in this country. They're made in volume. And also the work is ongoing in Johnstown Castle in terms of getting an emission factor for the blends, the high pK blends for the form of nitrogen is, again, it's a more sustainable fertilizer, and again has a lower carbon footprint. So look, Pat has spoke to us already about soil fertility levels, but look, I'll just hone in on, I suppose, look, something that's pretty close to my heart is the whole area of lime. Again, we have made good progress since about 2012 up to about 2016, 2017. We've seen some little bit of stabilization up to about 2020, but unfortunately for the samples that are coming into Teagasc, we are seeing that soil fertility is disimproving or declining out there on Irish farms. So again, that is a major concern. If we look at dairy farms, there's about 50% of our soils need lime. If you look at dry stock, there's about 65% of our soils need lime. So something as basic as lime, which can deliver many benefits, and I suppose it's the key that unlocks the whole area in terms of end use efficiency. So again, just to remind us here this morning, again, the target pHs. Grassland soils, we talk about a pH of 6.3 to 6.5. Clover multi-species, again, it's a level above 6.5 to 6.8. Tillage crops, again, 6.5 to 6.8. And look, the most effective form of lime in this country is ground limestone. And again, the big benefit on the grassland side of the house is that we can release up to 70 kilos of nitrogen per hectare per year from grassland soil. So this is an annual release or turnover of nitrogen, and this feeds into reducing our chemical nitrogen target, which we have done so well in the last 2 years. It also increases P use efficiency. Okay, just to draw yourself to this graph here. So again, this is some work from Johnstown Castle, and it shows the benefits of optimizing soil pH in terms of reducing emissions. So again, you can see there that we can reduce our emissions by 38% by optimizing the pH. So again, where we maintain those higher pHs, somewhere between 6.5 and 6.8, we can reduce our emissions by 38% in terms of nitrous oxide. So that is absolutely massive for a very low cost input that's basically, I suppose, the backbone in terms of soil fertility in driving nutrient use efficiency. Okay, just to, again, give you a few figures here. Again, what are our targets? What are our lime usage? Again, we've been using about 1 million tonnes in the last decade. In the last 2 years, in 22 and 23, when fertilizer got expensive, farmers done the right thing. They bought lime. We hit about 1.3, about 1.4 million tonnes. 2023 has been a difficult year in terms of weather, not a good year for lime. Again, industry estimate that we're around 750,000 tonnes of lime. But look, I'm very optimistic for 2024 that we will, we'll hit the 1.5, maybe even the 1.7 million tons of lime between now and Christmas. Just to remind you, our MAC target again for 2025 is 1.7 million tons. And as we move to 2030, again, we need about 2.5 million tons of lime applied on an annual basis. So again, we got to keep, we've a lot of soil test results on farm. We've hit 83,000 soil samples in 2023. And again, we must use that information as best we can in terms of applying lime and optimizing soil pH. In terms of the P levels, so again, you can see there has been an improvement in soil P levels. This is for the dairy soil samples. But again, there's still around, nearly 50% of our soils at index 1 and 2. Again, the sustainable index is index 3. And again, I suppose the positive story here, there's about 30% of our soils at index 4. So there's no need for P on those soils. In terms of potash, again, you can see there has been an improvement since about 2017. Again, I suppose the positives, we have a lot of soils at index 4. So again, there's no need for K. And again, I would think on a dairy farm, these are the grazing areas. So there's around 30% of our soils doesn't need K. And again, the sustainable index there is index 3. Okay. In terms of fertilizer use, so what's happened in terms of chemical P usage? So again, you can see since 18, we were quite good. We have used, the target. We're using somewhere around 46,000 tons of phosphorus. Our target in the MAC is 46,000 tons in terms of driving soil fertility. But you can see there in terms of the fertilizer crisis, since 2021, our fertilizer usage has reduced by 33%. The same in terms of potash. We've seen a reduction there of about 34% in the usage of K in the last 2 years. And again, that is a concern in terms of maintaining our building soil fertility. Our target in the MAC is 120,000 tons. So between 18 and 21, we were very much on track there. So again, we need to get back to applying sufficient levels of P and K. And again, very much around driving end-use efficiency on farm. So in terms of P and K advice, so again, you're probably familiar with this table. And again, I'll just draw your eye to the response to fertilizer. So you can see index 1, there's a definite response. Index 2, a likely response. Index 3, unlikely. So again, if you're at index 3, you know what I mean? You put on fertilizer there is very much on a maintenance basis. And index 4. So you can see there's between 25 and 30% of our soil is at index 4, and there's no response at index 4. So there's no need for either P and K. And as we move from index 1 to index 4, our soil supply increases. So again, maybe look, Pat brought this up on the first day. So again, look, there is parts of farms out there, depending on the system, that index 1 is fine in terms of biodiversity. Maybe there's low levels of productivity on the farm and you want to maintain the species, so you're not applying any extra P or K or lime. You're leaving the soils at that low fertility status to maintain that valuable biodiversity. But as we move up then, say, in terms of dry stock systems, look, probably index 2 was fine. If you had a good index 2 for both P and K, you'll probably grow as much grass as you want for that system. And again, as we move up the ladder in terms of index 3, again, we're looking at the more intensive systems in terms of grassland. So again, where there's high levels of nitrogen in the system. And again, look, index 3 is where we need to be for those systems. Okay, so again, a little bit as regards, why optimize soil P fertility. So again, work from Johnstown Castle. Again, long-term experiment in Johnstown Castle there, which show that we can reduce nitrous oxide emissions by 42% by optimizing soil P fertility. So again, at this stage, we have about half our soils at either index 3 or index 4. So again, we have lower nitrous oxide emissions from those soils. And again, another reason why we should build or drive or maintain fertility at that index 3 level in terms of a sustainable index, especially on the intensive production systems. Okay, so again, just as regards to maybe remind people as regards how much P and K is taken out. So again, if you take milk, for example, every 1,000 litres of milk, there's approximately a kilo of P removed and about 1.5 kilos of K. Again, meat, again, live weight gain, about a kilo per 100 kilos of live weight gain. Silage, about 3 to 4 kilos of P and about 25 kilos of K per tonne of dry matter. And again, in terms of grain production, we talk about 3.8 kilos per tonne of grain and 10 to 15 kilos of K. So that's offtake. That's what leaves either in the animal sales, in the milk tank or the bulk tank, or if you cut grass silage at harvest time, or when you cut cereals in terms of grain and straw leaving the actual field. So again, look, I just worked these figures up. So again, depending on your system and your stocking rate, you can see there, if you take maybe 2 cows to the hectare producing 10,000 litres of milk, there's something like 10 kilos of P and 15 kilos of K leaving in the milk or in the bulk tank. If you take, you know, say 2 finished animals there, 1,200 kilos of meat, again, about 12 kilos of P and 12 kilos of K leaving in, you know, at sale time or in the mart or in the factory, whatever the process may be. The same for sheep. Again, similar, 11 and 11, and again, cereals there. So again, if you take a 10-ton crop of winter wheat, you're taking out about 38 kilos of P and approximately 100 kilos of K. So that's offtake. So that's what we must put back to stand still. So again, if I bring this down to stocking rates, so again, you can see there, if you take a typical stocking rate of, say, around 2 livestock units per hectare, the removal there is 14 kilos of P and 30 kilos of K. So that's what's needed to drive the system in terms of milk and maintaining the animal in terms of P's and K's. And again, if you look for at maybe the livestock system, so again, you know, your beef and sheep. So again, I suppose the one thing for me that always, you know, is that the offtakes are quite low for dry stock systems. So if you take it between 1 to 1.5 livestock units per hectare, there's somewhere in the region of 6 to 8 units, 6 units of P and 8 units of K. Or even a little bit higher stock there, 2 livestock units, 8 and 12. So again, if you think about your 18, 6, 12, you know, it fits pretty well, you know, on an intensive dairy farm, you know, a little shy of 2 bags of 18, 6, 12, or on a dry stock farm, a bag to the acre of 18, 6, 12 will maintain your P's and K's in terms of maintaining soil fertility. Let's not forget about silage, one of the biggest crops we have in this country. The offtakes there, to remind you there, is something like 20 kilos of P and 125 kilos of K, and that's for a 5-ton dry matter crop per hectare. Okay, so again, I suppose you might ask the question, why build soil fertility? Okay, so again, index 4, we see a little response to applied P. As we move down the line to index 3, again, a little bit of a response, but generally flat. But then we see at index 1 and index 2, there's up to 2 tons of dry matter per hectare. So that's the yield response, so that's the benefit. And look, what's driving that is nitrogen use efficiency. So again, by having good soil fertility, we're using the nitrogen more efficiently, we're growing more grass. So 2 tons of dry matter turns into about 64 kilos of nitrogen per hectare of an efficiency by moving from index 1, 2 into index 3. So index 3 is very much the sustainable index. So that's where we'd like to have our soil fertility. So just to remind people then, so in terms of the build-up rates, so our standard build-up rates for phosphorus there is 20 kilos. At index 1, it's like a bag of Super P. Index 2 then is 10 kilos or 8 units. It's like a half bag of Super P. And then there's the extra P there that we have. You know, there's 50 kilos on index 1 and 30 kilos on index 2. And again, look, soil type is of major consideration. Like, you know, we talk about anywhere to move a part per million, we talk between 10 and 100 kilos of P per hectare. And to move an index, you know, or if you take an average of 50 kilos of P per part per million, or 150 kilos per index. So to move 3 parts per million of P, we need 150 kilos of P per hectare. In terms of potash then, so again, look, index 1, we talk about an extra 60 kilos plus maintenance, and index 2, 30 kilos. And again, in old money, that's 48 units or a bag of muriate at index 1, or 24 units at index 2, or half a bag of muriate. And look, K is a different nutrient completely in the soil. It's a lot easier to move your K than your P. So again, we talk about 1 to 2 kilos of K per hectare to move a part per million. So I suppose to give you an easy figure here this morning, like a bag of muriate, 50 units could move you an index depending on the soil type. So it's very, very easy build a K. So there's no excuse, there's no limit as regards K either, but it's very, very easy build our K. So timings of applications, look, the name of the game, Thomas will refer to this in terms of potash, but look, we're trying to get the nutrient out of the risky timings in terms of the early spring and late autumn, when we get a lot of, I suppose, soil drainage, possibly leaching, denitrification, and volatilization in terms of nitrogen. And we're trying to move into this more
2 minutes there, Mark.
Efficient window here. So again, in terms of the most efficient window, so again, we're trying to move into this sort of March to July time in terms of increasing end use or nutrient use efficiency on farm. In terms of phosphorus then, so if you ask me when should I apply my phosphorus, so again, the advice in terms of grassland is you're putting out 50% in the early part of the season, in your second or third round, and again, the remaining 50% in the fourth or fifth round. In terms of potash, again, my advice is, so again, you put out maintenance in the spring, about 30% of the K. You come back mid-season, about 30%, and then in the back end, another 30%. Look, Thomas will give us an update as regards what he's finding in his trials in terms of K. The role of slurry, so again, it's an on-farm, a very, very valuable nutrient. In my book, number one is silage field. So again, in terms of replenishing that valuable P and K, especially the K. Number two is if you're taking out heavy covers on the grazing block. So again, you're putting back in maybe 1,200, 1,500 gallons for every 5 bales of silage. And look, there's a bit of work, there's work going on by Patrick Forster here in Johnstown Castle. And Patrick is finding that if you want to build soil P, the most effective nutrient is organic P. It has what I say legs, or it lasts over a number of years. Where if you spread bag P, it very much does its business in the season of application. Okay, compound fertilizer. So again, this is some new work from Johnstown Castle. We will have new emission factor for our blends, our 18s and our 10s. So again, it's a more stable form of nitrogen, and again, this will feed into our inventory in terms of reducing our national emissions. Okay, so again, you have, I suppose, look, just a list of the products there, 18612, 18412. So for the grazing ground, we're looking for a P to K ratio 1:2. Anywhere we're cutting or removing a crop, let it be grass silage, maize silage, again, we're looking for the likes of a 13620, 10525, 15320. So a 1:6 is to P is to K ratio. Okay, slurry in my book should go one place, that's back onto the silage ground. That's where it belongs. Again, you're replenishing, especially the likes of the K, and also you're reducing the organic end loading, which is important in terms of water quality. But again, the K or the cattle slurry must go back onto the silage ground to maintain farm nutrient balance. So in summary, folks, look, optimize soil P, K, and lime. Again, the big driver is to increase end use efficiency. It'll also reduce our GHG emissions. And again, look, I'd strongly advocate here this morning that the slurry should go back onto our silage fields, especially to maintain the K. There's a lot of K in slurry, and also to reduce our nitrogen requirements. And again, in terms of fertilizer blends, again, the most sustainable products are a move to 18612, 13620 type products. So that's it for me. If there's any questions, I'll take them there now. Okay.
Okay, thank you very much, Mark. So look, we're going to do on the bottom of your screen there, you can ask some questions and answers there. We won't do any questions and answers now. We're going to do questions and answers towards the end. So in the meantime, I'll ask Thomas McCarthy to share his screen. So Thomas is going to do a little bit around the research he's involved in as a PhD student around potash use in grassland. So Thomas, I'll hand across to you.
Thanks, Michael. That's just showing up okay for everyone there, is it?
Perfect, yep.
So, okay, good morning, everyone. So today I'll be just giving a talk, I suppose, an update on the recommendations in terms of potassium advice on grasslands. And I'll also touch a little bit on some of my research that's come out of the PhD, both in outcomes we found here in Teagasc, Johnstown Castle, and in Solihull Research Farm. So I suppose just to start really, I suppose potassium, I suppose in recent years has maybe been overlooked as a macronutrient relative to nitrogen and phosphorus. I suppose it's not as environmentally sensitive, and consequently it might be overlooked a little bit, but really it's a key driver of plant yield. And just to touch on its functions in the plant, really it's critical for photosynthesis, and particularly in the gaseous exchange part of that reaction. So particularly where carbon dioxide is taken in and oxygen and water vapor exit the plant. And if we were to zoom in on, I suppose, the leaf of the grass plant, like any plant, there's these guard cells on the outer leaf, and these regulate gaseous exchange for photosynthesis. So really, when these cells are open, gas flows in and out, and this is when the water occupies the cell and these cells are open. And the role that potassium plays is in the closing of these cells, where it's used as an osmoticum to dispel this water out of the vacuole and to close the plant stomata. So really it regulates photosynthesis in that sense. So it's a critical from a nutrition point of view. It also plays a critical role in nitrogen uptake. So as many of you will know, nitrogen is taken up by the plant in two forms, both as ammonium and as nitrate. And where it's taken up as nitrate, which often tends to be the favorite form for nitrogen uptake, it stimulates the uptake of potassium, and potassium and vice versa stimulates the uptake of nitrate. This is because potassium is a positively charged ion in the soils and nitrate is negatively charged. So they're attracted to each other for maintaining electrical balance in the plant. So it plays a role in the physical uptake of that nitrogen into the plant, but it also plays a crucial role in the conversion of that nitrogen into proteins that are used by the plant. This is because the enzymes that are responsible for metabolizing nitrogen into proteins tend to be dependent on potassium for this to happen. So I suppose the practical consequences of that are maybe where you're growing silage to avoid high nitrate content in your silage, a good adequate supply of potassium is important to convert that into proteins that are of benefit to the ruminant. So potassium also plays a very good role in clover species. So, there's an adequate supply has been shown to be very positive for clover species, both in terms of growth and yield as outlined, but also in the development of plant roots and particularly in root nodules. So these are the housing for rhizobium bacteria, the bacteria in the soil and roots that fixes I suppose, inert nitrogen from the atmosphere into a form that can be used by plants. So, and as well as that, then those rhizobium bacteria have been shown to be positively influenced by a presence of potassium. And that's because the form that it fixes the nitrogen in is ammonium, and the uptake of this ammonium into the plant tends to be stimulated by potassium as well. So really we can go as far as saying that a deficiency for potassium in clover systems can severely reduce or even inhibit biological infixation. So it's a critical in that situation as well. So I think Mark kind of touched on this really, but just the current grassland recommendations for K, our soil fertility recommendation would be to maintain a soil K index 3, which is 100 to 150 milligrams of K per litre in your soil test result. And at that optimum range, we'd recommend just to maintain the soil K fertility in this range then, and that would be 30 to 35 kilograms of K per hectare, depending on your stocking rate to maintain that optimum level. And as we progress down into suboptimal indexes, we'd add another 30 kilograms per drop in index, and that's really so we can build back up into that optimum range. Similar system on the cut swards, maintain the same index, soil K index 3. However, we can see here now that the recommendations for fertilizer input are much higher, and this tends to be because there's much higher offtakes in the removed or harvested silage from the sward. So on a typical 3 or 4 cut system for silage, on an intensive system, you're even at index 3, your offtakes could be in excess of 300 kilograms of K per hectare. So that would be the recommended rate over the year, and adding 30 kilograms per respective drop in soil K index thereafter. So I suppose what I'm driving at really is that on these grass silage swards in particular, there's a very large requirement for K in order to, I suppose, compensate for what's being removed, and it shouldn't be overlooked really, especially on a cut sward system. So just some, I suppose, previous research done here in Johnstone Castle, looking at ryegrass yields in response to fertilizer K input, we can see that there's a very positive relationship between additional fertilizer K input and yield. And we could say from these findings over a course of a few years that for every kilogram of K fertilizer input, we were getting a return of 6 kilograms of dry matter grass back. That's not the full story. However, we need to bear in mind with excessive potassium application, we can run into issues with luxury sward K uptake. So really it's a tendency, particularly in grass species, to, I suppose, to mine out excessive K more than it requires for normal growth. And this can depress the uptake of other cations such as magnesium and calcium. And I suppose a deficiency then in magnesium during the grazing season, you could run into issues with grass tetany. And in grass silage, I suppose a deficiency in calcium can lead to high K silage with problems with milk fever in the springtime. So we look at the mineral balance constituents in the grass for magnesium, calcium, and its relationship with potassium. And we can see from that graph on the left from previous research that where this ratio in the herbage goes over 2.2, the incidence of grass tetany can increase exponentially. but we also use just the K concentration on its own as a percentage of K in the dry matter as an indicator of grass tetany. So with this in mind, what are the optimum timings for K to the sward? Well, that spurred us on to set up this experiment in Johnstone Castle, where we ran it for 2 years, looking at the role of the background soil K index and the application strategy to the sward and how it optimized grassland yield and herbage quality. So we had 3 levels of soil K index, indexes 1, 2, and 3. We had a simulated grazing regime on these plots, and we evaluated 3 different application strategies of K to the sward, both as a spring compound fertilizer, so typical as your 18-6-12 in the spring. We also looked at slurry as a K source in the spring. And then we also looked at autumn K fertilizer as a back-end application, and we looked at how they affected yield and soil K uptake, or grass K uptake. So some of the findings coming out of that, just to say that on the index 1 and 2, these soils got their prescribed maintenance plus build-up rates. So 95 kilograms of K going out on index 1, 65 kilograms of K going out on index 2, and then on those index 3 soils, they received the maintenance rate of 35 kilograms per hectare. So just to draw your attention to the yield, first of all, where we were in index 1 and used that higher rate of build-up, we were almost able to compensate for the optimum range of soil K index 3. However, we did see there was a yield penalty of about a tonne per hectare between having build-up rates at index 1 versus just maintaining our optimum soil K index 3. So while that's not significant from I suppose a research point of view, like it's on a practical level, an additional tonne is significant at farm level. So really, it just shows there's no replacement for being in that soil K index 3. However, we see that the background rate of soil K fertility was a big driver of luxury K uptake. And we can see that being in that index 3, you're getting much higher sward K uptake in terms of an extra 100 kilograms of K per hectare being taken up by the sward at index 3 versus being down at index 1. Looking at that trend again across the season, if we look at the 3 application strategies and having your build up at index 1 and 2 versus maintaining index 3, we can see that we can run into issues during the grazing season with having high K in the grass, and that could be an issue maybe where you're on a farm with historic problems with grass tetany and that. But on the other side of it, being down at that index 1, particularly at the autumn K, we can see that we can run into problems with maybe deficiency of K in the herbage. Like generally, we say less than 2% of dry matter K would you'd be running into deficiency with the amount of K in the grass. So really it's about maintaining it between the lines between 2 and 2.5% of your dry matter. However, as I said, on farms where there might be problems with tetany and you want to get up into a more optimum level, we do see that autumn K is a good strategy in terms of getting up your build up without running into issues with tetany in the following year. Just to draw your attention then to some research that we did in Solihull Research Farm. So I conducted an annual farm K balance for the farm gate over time for Solihull Research Farm. I had long-term data sets from 2005 to 2022. And how we calculated the balance for the farm for potassium is we got the sum of all the potassium that entered the farm. That would be in fertilizer, animal feeds, livestock purchases, and then an element of atmospheric deposition. Then I got the sum of all the K that exits the farm. So that would be the K in your milk sales, livestock sales, and then K lost to leachate in groundwater leachate. And the balance then would be taking the entering from the exiting and resulting in a balance for potassium per hectare per year. And this is then related to the annual change in soil test K across the farm for the year. So some results coming out of that. I just honed in on the data from 2016 to 2020 as the farm was in a build-up phase for improving our potassium levels on the farm. And we can see that milk production and the K leaching to groundwater were the most significant sources of farm K depletion at this time period. And over this period, we had an average fertilizer K input of 98 kilograms of K per hectare. As I said, this was to build up our soil K fertility up into the optimum range. And we were able to calculate that in order to maintain that level of 85 milligrams of K per litre that we had in 2016 over these few years, it would have taken a surplus of just 20 kilograms of K per hectare to avoid declines in soil K fertility. And over this same period, to get up into a midway of index 3 at 125 milligrams per litre, this would have taken a fertiliser K input of 115 kilograms of K per hectare. Just a side note then on some of the cut swards where we have grass clover in the system in Salahead. We looked at the relationship between fertiliser K input and sward clover percentage as percentage of the dry matter. And we can see very positively that the proportion of clover in the sward increased in line with additional fertiliser K input. It's important to note, however, that the initial soil tests K results were in index 1 here, so we would expect any positive in terms of additional fertiliser K. And as well as that, most of that K would be removed from the sward again as it was cut and removed, and we had a fertiliser use efficiency of about 70% there for the K, so large removals again off the sward. Just in terms of some fertiliser K advice, some timings for fertiliser K in the grazing platform. So really, I suppose it's well known at this stage we want to try and get into index 3 and to maintain that level of soil K fertility. So the way we would objectively aim to maintain that would be to use 2 bags to the acre of 18612 in the second or third round. Where you're in a build-up then with index 2, you'd be following that with another 2 bags of 18612 to the acre in the fourth or fifth round. And where you're in index 1, we'd recommend an additional half bag to the acre of muriate of potash after you close off in October for the winter period as an autumn K application. So generally there's lower requirements for K on these graze swards. That's largely due to the majority of that potassium being recycled back onto the sward in the urine and dung by the grazing animals. So consequently the requirements are lower. On the silage fields, however, it's a different story. We see that, again, we want to maintain index 3. However, the requirements are higher here because of the larger offtakes. So really, with that optimal soil K index 3, we'd recommend 2.5 bags of 0730 to the acre in an early spring application. So really, from around the start of March to now, really, as soon as it's practical to travel the land, we'd recommend getting that out. And where you're in index 2, we'd follow after the first cut silage with an additional bag to the acre of 0730. And where you're in index 1, that would be another 2 bags of 0730 after that first cut in order to build up into optimal range. So really just to drive home those large offtakes on the cut swards. Where you're using slurry in the system, where we're in index 3, we'd recommend 3,000 gallons to the acre in an early spring application. Again, as soon as it's practical to travel the land, get that slurry out and get your K requirement out in the slurry. And where you're in index 2, you'd follow that after the first cut silage with 1,500 gallons to the acre, or when it's index 1, an additional 2,000 gallons to the acre. And it's important to note to just avoid more than 90 kilograms of K in the springtime. That's again to avoid that high K silage and running into issues with milk fever, for example. And really, I suppose what I'd like to drive home is that it's very important to target fields with low soil K fertility and not just, like the pet fields, the ones that are closest to the yard or the easiest ones to get to, because we do see on farms across the country that where there's large offtakes on the outblocks, that silage isn't, or that slurry isn't necessarily going back to those paddocks, and we're running into issues with dropping fertility levels on outblocks where silage is taken. However, fields around the yard, or the ones that are easier to get there, can run into high index 4 very quickly where there's a lot of slurry put out on the system. So really it's about targeting fields for slurry based on your soil test results. So just to conclude, on cut swards, maintain index 3 and maintain that with a maintenance regime. And I suppose as a general rule of thumb, we'd say for the fertilizer program, for every ton of expected dry matter, 25 kilograms of K per hectare would be the recommended rate. And obviously to combine your fertilizer regime with your slurry, it's a very valuable on-farm resource, and to target those fields with the low soil K fertility. On the graze swards, then we do have a lower K requirement, as I said, due to the nutrient cycling from the urine and the dung. Again, aim to maintain your soils in index 3, and where you need additional K in terms of build-up, look at your soil tests and apply accordingly. And again, slurry can be an efficient way to supply K requirements in that sense. I just want to say on a side note from some ongoing research that we are doing here in Johnstone Castle that it's not a one-fits-all scenario for potassium fertilisation requirements, that, lighter soils, they don't have those sandier, well-drained soils don't have the capacity to retain K as much as, say, heavier, poorly drained soils. And it's maybe more important to follow a little and often requirement on these soils over the year to minimize the leaching. And however, then on the heavier soils, we do see that there is a greater capacity to store K and resupply in that situation. So really, I suppose it's about knowing your soil type and acting accordingly from there. So that's it really. So thank you very much, and I'll be happy to take any questions.
That's brilliant, Thomas. Thanks very much. You got us back nicely on time. So look, thanks for that. There's loads of information in there, and again, just for everybody, the Q&A part of the in terms of asking a few questions to Thomas, we'll take those at the end. So next up, we're going to have Veronica. So Veronica, you might share your screen. Veronica, you're going to talk and maybe expand a little bit more on the organic manures that were touched upon in the previous two talks. So Veronica, across to you, if you can share your screen.
So look, I'm here to talk. Mark was speaking about the how we need to change or move away from our heavy reliance on chemical fertilizers. So I'm here today to talk a little bit about maximizing our use of organic manures as an alternative nutrient source on farms. So I'm going to be talking about the nutrient content of the manures to start with. And then I'm going to be talking a little bit about how to use them to maximize their efficiency on farm through timing and method of application, and finish up hopefully on time with where to use them on the farm and how best to distribute them on your system. So I'm going to start with just putting up this table here. This is taken from the nitrates directive, and it is the nutrient content of all the different manures, their total nitrogen content, their percent nitrogen availability, and finally their total phosphorus. The two I just want to highlight before I continue are the first one, cattle slurry. So these figures are based on a survey that was done in 2013 for beef and dairy enterprises, and that figure has actually changed since 2022, when it was at 5 kgs of per ton of total nitrogen at 40% availability and 0.8 of phosphorus. Why it's relevant is it means that if people are looking to export manures to bring their stocking rate under the 170 range, they're now having to export more for nitrogen to reduce their nitrogen load. I come from the tillage side of the house, and I suppose I'd just be highlighting from our side as importers, potential importers of organic manures, that the balance between the nitrogen and phosphorus has changed as a result of those change of numbers. And to just be aware that if you were importing before, per kg, now you're importing 1.3 times more phosphorus with every kg of nitrogen. The other one I just want to talk a little bit about or highlight, because it's changed a lot in the last 2 years, is the broiler and deep litter, because it has jumped from 11 kilograms per meter cubed of total nitrogen up to 28. So it's quite a substantial jump there. If people were using it consistently in the past, they may not be aware that it has changed a lot. And just to highlight that these are these are total nitrogens, 50%, you can see there in the broiler rate, 50% of that nitrogen is available at application for plant use. The phosphorus is considered to be 100% available unless it is applied to a low index soil of 1 or 2, and then it is at 50% availability. So, it's because the soil itself is essentially taking a pull or drag off it, and much like Thomas said there about potassium, 90% when reduced or put it onto, we consider it 90% for available when we put it on a low index soil. But the reality is what you get on farm isn't necessarily the same as what's on those tables. That figure, that cattle slurry figure, is based on a 6% dry matter slurry. And we know dry matter has been correlated with nutrient concentration in the past through a study done in the 70s. The reality is what you get on farm may not be at 6% dry matter. So ideally, if you're using slurry for, and you want to use it as a replacement of nutrients that you're off taking, ideally you would like to be testing that slurry. I just want to point out that you can buy a slurry hydrometer. It's not 100% accurate, but it will give you a rough indication of the dry matter. It's a weighted device with a gradient on it, and you can see there in the side photo that you settle it, you put it into the slurry, and as it settles, it'll give you your percent dry matter. In this case, this particular slurry was at 4% dry matter. When you know that dry matter concentration, then you can relate it back to the concentration of nutrients in the slurry. So you can see there a table that shows us that the 6% dry matter, as I discussed, is 2.4 total nitrogen at 40% availability, giving us 1 kg per ton, 0.5 of phosphorus as long as it goes on an index 3 soil, and 3.5 kgs of potassium. But were it to be only 4% dry matter, all those figures drop. So we're at 0.7, 0.35, and 2.3. So, you know, just to be aware that whatever you're putting out, you know, you're running it off that it's at 6%, and if it's not, you're not actually going to get the value for the slurry that you'd hoped. So just to summarize, 6% dry matter slurry, we consider it to be the equivalent of bagged fertilizer at 9,532, and that is a value of €29 per ton, per 1,000 gallons, sorry. So then if we accumulate or spend, you know, per 1,000, just multiplying it up, you can see there an application of 6.3% dry matter or cattle slurry applied using low emission slurry spreading on an index 3 soil. You're talking about 34 kilograms of nitrogen per hectare, or 27 units of nitrogen per acre, 19 kgs per hectare of phosphorus, or 15 units per acre, or 120 kgs per hectare of potassium, and 96 units per acre. So a substantial, you know, input of nutrients for the 3,000 gallons. But its efficacy really depends on its time of application. This is a similar diagram that you saw Mark use earlier, and it's just showing that the grass growth curve for the different soil types. So well drained obviously has a little broader on the shoulders of the ear versus a poorly drained soil. And really, if you're putting out the slurry, you're assuming those figures that I gave you are kind of based on using it in the springtime when it's most effective. If you start moving it to the shoulders of the year, your efficacy is significantly reduced. And the agricultural catchments program would have shown through their research on slurry applications of slurry that 43% of the total P loss and 45% of the oxidized nitrogen loss occurred in the 3-month slurry closed period as such. That's taken from research published in 2016. So really, you know, again, in a tillage system, we probably wouldn't have been using our organic manures as effectively as we could. This graph here shows the nitrogen response curve on a tillage system. And as you can see there, up until around this time of the year, the soil really is supplying sufficient nitrogen for the growing crop. And it's only when it gets into stem extension and up to the point when it heads out that it needs substantial amounts of nitrogen. After it heads out, the requirement reduces again. And this is a significant problem in a tillage system because, as you can see here on the bottom graph, the soil supply of nitrogen is building based on the application of the nitrogen that isn't used by the crop, and also the potential oxidizing of organic nitrogen in the soil, making it more plant available. So we come out at the end of harvest with a soil reserve of nitrate nitrogen and no crop that's in the ground using it. And traditionally, what we would have done at this point is probably applied some kind of dungstead manures, ploughed it in, and sowed our winter crop. The winter cereals don't, as I said, they basically don't need a lot of nitrogen over the winter. So this meant that we were losing substantial amounts of nitrogen over the winter period. Catch crops have significantly helped in reducing those losses and have the potential to reduce the losses of cover crop by up to 86% of the nitrogen load in kgs per hectare. But what we're seeing a lot of these days is people moving to using the umbilical slurry applied to a standing crop, which is tying in with what's the grassland system model, which is applying to the growing crop at the time it needs it most. So I suppose the messages we would have in relation to maximising nutrient recovery in the use of slurry is to try and have 70% of slurry out in April. Not to put it out in soil conditions that aren't suitable, so saturated soils, frost or snow covered ground, because it simply doesn't infiltrate into the soil. when heavy rain is forecast, and also the best weather is that cool, overcast, dull weather. Avoid really hot, dry days. If we're trying to reduce volatilization, the ideal is to try and reduce the dry matter by about 1%. By reducing the dry matter by about 1%, we're reducing volatilization by 5 to 8%, but you will be diluting your P and K content because, as we stated earlier, dry matter relates to the nutrient content. And finally, using low emission slurry spreading techniques. So this relates to what Patrick Forstall was speaking about last week, so I won't dwell too much on it because I know I'm already behind time. But essentially, to maximize the slurry nitrogen, the use of slow trailing shoe technology as opposed to splash plate is very effective, but also the time of the year. You can see there by applying with splash plate in the spring as opposed to the summer, by applying in the summer, you lost 54% of the nitrogen. But relatively speaking, spring applied trailing shoe, it gives 9 units of nitrogen, as opposed to spring applied splash plate is only 6 units of nitrogen. So essentially the trailing shoe, the loss of 35% as we move from splash plate to trailing shoe. So essentially it's all about maximizing the slurry, putting it out at the time when it's most effective, and with the technology that maximizes its how it's kept in the soil and utilized by the soil and the plant. Other benefits of using low emission slurry spreading, we have the dribble par and the trailing shoe. Obviously it increases your flexibility when it comes to application rates. You can go out on heavier covers because the trailing shoe will part the grass and put the slurry underneath the grass canopy, which protects it from the atmospheric loss. But it also reduces the grass contamination, means that you're getting more precise application of nutrient, greater flexibility, less pressure for trafficability. You can wait a little bit longer for the field to dry out, and you can spread on higher covers. So there's a lot of positives as well as the nutrient retention. So the final question that I was here today to talk about was, where should the cattle slurry go? And as Mark pointed out, the whole concept of the closed or the holistic system is that the nutrients should go from whence they came. So, grass slurry is applied to silage ground, the grass is harvested, and that harvest is fed to cattle, which produce more slurry. Hence, it's a closed circuit. Really, silage is ideal for the use of slurry. Grass dry matter removes 4 kgs of phosphorus and 25 kgs of potassium per hectare, which works out at a ratio of about 1:6. And that is the perfect ratio for slurry. It's well balanced. So in this table here, I've just put in the offtake. So you can see there, oops. You can see there that the offtake for a production of a 5-ton crop of first cut silage and a K index 3 soil is approximately 80 units of nitrogen, 16 of phosphorus, and 100 of potassium. And 3,000 gallons, as I mentioned earlier, contains 27 units of nitrogen, 15 units per acre of phosphorus, and 96, leaving a balance of, we're pretty much taking care of our P needs and our K needs, and we have reduced our nitrogen down to a balance of just 53 units. So it works really well in the silage system. For grazing ground, it's not as ideal because the ratio is more 1:3. So the cattle slurry is poorly balanced for that system, and we do tend to get the excess K, luxury K uptake, and the whole issue with the grass tetany that Thomas referred to a moment ago. So really, in this scenario, pig slurry becomes ideal as it's a more suitable balance to the system. So just to finish up, this is taken from a nutrient management plan prepared for a client of mine who's in a mixed beef tillage enterprise. You can see there the grassland stocking rate on this farm is 100, just under 130. There is 63% of the farm is in grassland and 36% in tillage. The fertility status of the farm is given there, and you can see that there is a P issue on the farm. 37% of the soils are index 2, and approximately 12% of the soils are index 1 for potassium. So look, this is a real fussy slide, but I'm just going to zoom in here. This is kind of a close-up for the first few splits applied. And I totally agree with Mark. It's a closed system, and the application of slurry onto silage ground is the ideal. However, in this situation, the slurry was going on the same silage ground repeatedly, and it resulted in the pK indexes of these particular fields to increase to the point where pK is in excess, or it's index 4. And at this point, what we'd be recommending is that you start looking at your low P and Ks. And you can see here in this situation, there is some grazing fields that have dropped to an index 2. As we said in the previous slide, there is a pK issue in some fields on the farm. Again, a one-cut and grazing system. And even a spring barley field here that is a 2 and a 1 for P and K. And really, I suppose it's not to close your system to potentially using slurry on these lower index soils. Finally, just as well to acknowledge the capacity of the soil. Slurry is not like bagged fertilizer in the sense that it moves, it's watery, it can move very easily. So knowing what your capacity of your soils are before you apply slurry is important. These are taken from the EPA PIP maps, the pollution impact potential maps, and they can be, clients in Teagasc, we can produce them as part of your nutrient management plan. You can see here, this is a nitrogen PIP map. And where the colors are darker, it indicates that the soil is more at risk of losing of nitrogen loss. And that may be due to the soil type. It may be due to the management system on the farm. There's a couple of factors, topography, a couple of factors that could come into play here. But you can see here, these are all parcels or fields on this farm, and there are certain fields are darker in color, so they're higher risk of nitrogen loss than others. And just to be aware when you're applying your slurry, particularly if you're moving into a risky part of the year, just to keep an eye on these maps. Again, we have the phosphorus PIP map here, and you can see these darker colors here are all high risk for phosphorus loss. And this brown coloring here would indicate that these soils are peaty by nature, and peats are very poor at storing phosphorus. So when applying slurry, on this farm, you'd be very conscious of the fact that these soils here are high risk for phosphorus runoff or phosphorus loss into a watercourse. And this final PIP map shows us where the potential movement of the phosphorus is. These are the overland flow kind of pathways and the discharge points, and the brighter red ones indicate they're very high risk for nutrient movement. So you can get these diagrams for your farm, produced for your farm, and it just gives you a better understanding of the limitations of your farm, where the risk areas are, and allowing you to use your slurries more effectively as an alternative to replace to chemical fertilizer. And just before I finish, just to mention a couple of regulations in relation to slurry. People are probably aware of a lot of these already, but just to be aware that from the 1st of January this year, holdings with a grassland stocking rate of over 130 kgs of nitrogen per hectare must use low emission slurry spreading. Dropping to 100 kgs of nitrogen per hectare from next year. So anyone next year with a grassland stocking rate of over 100 kgs of nitrogen per hectare must use low emission slurry spreading to apply slurry to the ground on farm. From the 1st of January 2023, it was mandatory that all livestock manures applied to arable grounds had to be done using low emission slurry spreading or incorporated within 24 hours if applied in any other way. And pig slurry also has now to be spread by low emission slurry spreading. Just be aware there's a TAMS grant available. However, the terms and conditions are when it becomes mandatory for you to use low emission slurry spreading, you tend to get eliminated from the grant availability. So I would be recommending anyone who is currently kind of under the 130, but likely to be over the 100 kilograms of nitrogen per hectare in 2025. This is the time really if you want to avail of the TAMS grant for a low emission slurry spreading equipment. And also, just because I think we talk a lot about buffer strips, people think everything is 3 meters now. Be aware that the buffer zone for organic manures is 5 meters, and for the 2 weeks on either side of the closed period, that moves to a 10-meter buffer strip. So just to finish up, just to highlight that organic manures are a valuable nutrient source on, I've tillage systems read there, sorry, that's all systems. It's worth testing to determine the nutrient content of them if you can, and the hydrometer is cheaper than getting it tested in labs. So, it might be something if you're importing a lot of slurry, or, you're worried about the slurry being too watery, it might be worth the investment. They're not very expensive at all. It's a case of right time, right place, and right rate when it comes to slurry, and just knowing where your limitations on your system are and working around that. And finally, they can be a cost-effective way of addressing low phosphorus soils, while ideally you rotate it onto silage, but it's worth looking at where your low P soils are, as slurry can be a cheaper way to build back up phosphorus compared to chemical fertilizer. So thanks for your attention.
So look, we are going to move on to maybe talk a little bit more about slurries and how amendments can improve them in terms of an environmental thing. So Veronica, I might just get you to stop sharing, and I'll invite Dominika to come in next. So it's a little bit there, Dominika, about the emissions from, or hopefully the reduction from some of these slurry additives. So away you go.
Hopefully, thank you very much, Michael. Can you see the right screen there?
Perfect, yeah, we can see it. Yeah.
Perfect. Okay, so thank you very much. So look, I'll move in a slightly different direction from the previous speakers, and it's maybe a little bit less on soil fertility, but I think soil fertility is implied through the best use of slurry as a very valuable resource, as everyone before me mentioned. So whenever we talk about slurry management, there's inherently in a biological system, there are going to be some emissions associated with management of the material. And really, it is about reducing those losses and the best management possible. So slurry additives in particular are getting very popular in the last few years, so we'll just spend a few minutes on those. So I'll talk a little bit about emission targets, so basically why and the background of this work, and the sources of emissions in agriculture, and then take you through the additives research. So my talk will be very much kind of research based to show you the latest, what we've done over the last few years, and give you the flavor of how the work is being done and what kind of results we're getting. So we'll talk through some of the screening trials and scaling it up and downstream emissions. So when we talk about additives, we're mostly concerned with slurry storage. But at the same time, when that slurry is amended in storage, what is going to happen when that slurry is further land spread? I'll show you an example of a pre-commercial application with one of the slurry additives we've worked with, and just touch on other pre-treatments. So starting with the reduction targets, look, many of you have heard it over and over again, but those targets are not going away. And at the same time, we have the legislative targets, and we also have the loss of nutrients from slurry. So it really makes sense to keep that in mind whenever we manage slurry. So we have ammonia targets and greenhouse gas targets. So ammonia is not a greenhouse gas, it's an air pollutant. It also indirectly contributes to greenhouse gas emissions. So it has bearing on both sides. And while we've over a limit of greenhouse gas emissions of 42% by 2030, which that's gone up from it used to be 30%, so it's gone up. At a national scale, the agriculture has its own target, a national target of approximately 20% or 22 compared to 2018. Okay, so there's loads of targets. There's a few targets there, just to bear that in mind. But they all lead kind of to the same landing spot. So in terms of the sources of ammonia and greenhouse gas in Irish agriculture, on the left-hand side, you see these are the latest figures from EPA from 2023. So their calculations are always 2 years behind. So we haven't seen the 2022 figures yet. But on the greenhouse gas side, approximately 10% of agricultural emissions come from manure management. That's mostly from methane, CH4, and also from nitrous oxide and 2O. Okay, so that 10% is fairly substantial if you think about just animal housing and slurry storage. But even more so on the ammonia side, manure management is half of all the ammonia that we emit in Ireland. And if you think about the relatively short housing period in Ireland, and also then a lot of slurry spreading occurring in spring, so clearing those and emptying those tanks relatively quickly as possible. From that part of agricultural management, that part gives rise to a lot of ammonia emissions, and that is a large nitrogen loss. So there are really the two sides of the coin of why to reduce emissions. So with that, if you think about slurry research and additives research, it's not really that straightforward. So you see in the top left corner, we start with kind of smaller scale incubations, then moving on to larger incubations, then in the bottom corner. But at the same time, there's also a question of downstream emissions. So hence there's plot trials and field trials that are indicated on the right-hand side. So it's actually not a trivial a task to assess an additive. So starting with screening at that smallest scale, we would have worked with slurry over the last few years. And first of all, what's known in other countries is that chemical acidifiers, so the various acids, are used to reduce slurry pH, and that keeps more ammoniacal nitrogen, so that nitrogen that's available to plant, but also available for loss. That pH shift makes that nitrogen more stable. Okay, so it moves it from ammonia to ammonium fraction, and that makes it more stable then, reducing emissions. So in storage, we've seen that emissions can be abated by over 90% from a variety of different acids. Okay, but acids might not be easy to work with. And they need to be purchased on the farm, and there's also, there's other considerations such as health and safety and the whole infrastructure associated with them. So the follow-up question we had was, well, what about waste products, any kind of byproducts of agricultural and food industry? Could they be used? Could they do the same thing? And I appreciate there's a lot on this slide. So what you see here is the four graphs. The two top graphs indicate ammonia emissions, and the bottom graphs indicate methane emissions. And we looked at additives that were kind of waste products. So they either were acidic in nature, so they already had low pH, or they would lead to a lactic fermentation in slurry, therefore creating lactic acid and a dropping pH, acidifying, kind of bioacidifying slurry this way. So from those graphs, you see there was a lot of amendments that we worked on. In a nutshell, when it comes to ammonia emissions, some of the sugar beet molasses, apple pulp, and grass silage effluent reduced emissions, but that wasn't necessarily the same amendments that were the best for methane. So for methane, it was spent brewers' grain, also sugar beet molasses, and the grass silage effluent. However, there was also a variability there in terms of what inclusion rate those additives were at, and some of them needed to be at a higher additive percentage to work. So while some of them were promising, it's not a very easy kind of route of delivering additives in terms of how much and how consistently they will work. And that's why further down the road, we also looked at commercial additives that are available on the market. This study is currently under review. I'm showing you methane results because there were no effects on ammonia emissions. That's why I'm not showing those. But in terms of methane, you will see that there are some products. So this is our control here, the second from the left. Sulfuric acid, which is one of those chemical acidifiers that we know that works well. Except for sulfuric acid, there are a couple of commercial additives here that have shown so promise in terms of reducing emissions. So this is definitely something that need to be looked at further, and there is a good promise there. So scaling those small scale incubations a bit further in one of the projects I recently had, we worked at that kind of 20-liter slurry scale, and again looked at ammonia and methane emissions. So that's represented by the two graphs here over winter storage. So we've tested again a number of further additives that are becoming available or popular. Instead of sulfuric acid that we've worked with before, we tested alum, which is aluminium sulfate, and it's also a chemical acidifier. We've looked at lactogypsum, which is a byproduct or waste product of dairy industry, zeolite, a couple of commercial products, biochar, dairy processing waste, and ammonium thiosulfate, which is the chemical that was previously investigated by Teagasc in the 90s as a potential urease and nitrification inhibitor, and could it potentially reduce ammonia emissions? So on the ammonia side, you see that alum, lactogypsum, and zeolite significantly reduced emissions. On the methane side, it was alum, lactogypsum, and ammonium thiosulfate. Okay, so there were two amendments that were common for both gases, which was alum and lactogypsum. So we wanted to take two of them into further testing at a larger scale. However, we've encountered problems. Alum, how good it was at reducing ammonia emissions, it created a really thick slurry crust to the point where we deemed that slurry unworkable in an on-farm setting. Because to break through that slurry crust, that would require much more working in terms of agitation, and could it potentially be an additional health and safety hazard in working with that thick crust. Therefore, from chemical acidifiers, alum work very well, but sulfuric acid might still be the kind of preferred amendment. On the lactogypsum, which was very promising, this was material we obtained through another research project, and unfortunately what happened was lactogypsum became unavailable to us. So what you'll see in the next slide for that larger scale tanks that we have here in Johnson Castle, we had to pick slightly different amendments. So as I said, instead of alum, we went back to sulfuric acid as the kind of tried and tested option. Instead of lactogypsum, we decided to test ordinary gypsum, slightly different material, but some of the characteristics are similar. And we had one last slot left in the trial facility. We decided to go for biochar for one reason. Over the last few years, we've been getting a number of questions on biochar, and we're hearing from farming community, from practitioners, that this is really of interest, and they want to know, is it effective? Will it reduce emissions? Will it perhaps increase their carbon content of the soil due to the material characteristics? So for that particular reason, we brought it forward in that trial. As you can see, emissions were fairly low anyway. So on the ammonia side, we only had a few % loss, most likely due to a relatively cold winter. So our winter storage conditions were quite cold. But again, sulfuric acid reduced emissions. Biochar wasn't significantly different from control. However, there seemed to be a trend for potentially reducing emissions. And similarly, on the methane side, sulfuric acid reduced emissions, biochar reduced emissions slightly, but we've also seen gypsum. So it didn't reduce ammonia emissions, but it did work on methane. But again, it's not, it's not really the original product that we were hoping to test. With that in mind, then we need to ask ourselves what's going to happen with downstream emissions. If we reduce emissions in storage and we're retaining that additional nitrogen, are we going to see any increased emissions? With that in mind, we carried out a plot experiment measuring ammonia emissions, greenhouse gas emissions, and we also looked at grass agronomy. So with that, we had 3 applications of slurry with or without amendments. So application 1, 2, 3, and what you see here is ammonia emissions associated with that application. And in all applications, slurry with sulfuric acid exhibited the lowest losses compared to unamended slurry. So, and that was the kind of consistently performing amendment. Gypsum showed reduced emissions in the first application, but not in the second application. In the third application, I know it says non-significant here, but that is due to whatever happened to our slurry treatment. There is a huge internal variability in between the replicates in that particular treatment, and that's what's driving the not being able to detect significant differences between them. So that merits further investigation from the project team. The project is still ongoing. That's why I can't give an exact answer yet. Then we also looked at, as I mentioned, looked at greenhouse gases. So on the nitrous oxide side, which nitrous oxide would be the main greenhouse gas of interest after slurry land spreading, so methane in storage, but nitrous oxide on the field. We would have maybe expected knowing from previous literature that sulfuric acid can reduce ammonia in storage, but it might increase nitrous oxide emission after slurry land spreading. However, we didn't see that. So we had a relatively low emissions from land spreading, and slurry emissions were the highest compared to the other treatment, the biochar treatments. Biochar, gypsum, and sulfuric acid were all lower than slurry. And we compared those with protected urea. Could have picked CAN, but we thought protected urea is the fertilizer that we are, we would favor over CAN because of reduced greenhouse gas emissions, and also would favor them over straight urea due to reduced ammonia emissions. So really, as kind of as a industry standard, hopefully going forward into the future, that's why we compared with protected urea, which losses from protected urea are usually fairly low. Okay. However, why am I going back to storage emissions? So this is a quick stop tour over slurry amendments work in the last few years. And what we're seeing there, what falls out is that chemical acidifiers and other materials that are acidifying slurry, lowering its pH, are effective in reducing emissions from storage. However, more and more we're talking about anaerobic digestion and co-digestion of slurry with other feedstocks. However, we can't use acidified slurry in AD. Therefore, there is a need for a completely other additives that are not going to impede AD processing. And that's where some of our research comes into with University of Galway, where we looked at oxidative type of treatment at reducing emissions. And we're looking primarily at methane, to reduce methane during slurry storage pre-AD, so that the methane is preserved for the AD process. So it's a win-win situation both for AD and for agricultural emissions. So we've looked at the impact of concentration and frequency of addition to kind of tailor that treatment. Then we moved it on to a larger scale. And what happened was, while we had a really good reductions in the smaller scale, those reductions were still seen, but not to such an extent at a larger scale. So on the left-hand side here, you see that the red and blue the treated slurries are both below control levels. On the right-hand side, you see ammonia emissions. And unfortunately, it is very difficult to get an amendment that works on both gases. And here we see that the two kind of formats of slurry additive that we tested, they both ended up above control. However, the blue treatment, if you see, it's below control for over 60 days. So this was if that treatment was being repeated maybe more frequently after that, or if the slurry storage pre-AD was kept to a short period, then that additive was still very effective at reducing methane emissions, but it was also effective at reducing ammonia emissions. And that particular treatment is being tested further at a pre-commercial scale. So you see some of the elements of the setup that University of Galway, in collaboration in a collaborative project with us, are testing on one of the farms. And it's a very easy retrofit into existing slatted tanks, where you see the kind of piping going into the bottom of the tank to dose the amendment from the bottom, and the whole system has a very easy kind of dosing setup. So when you think about, for example, slurry acidification, you might have heard from other countries the issues associated with kind of the whole setup and infrastructure required for that. But here you can see a very, very easy setup to introduce amendment into the tanks. And I'm aware that I'm running out of time, so I think I need to stop. I'm pretty much finished anyway, but just wanted to literally just put up one slide to show a different and other slurry pre-treatment, such as separation, plasma acidification, AG I've mentioned, and in-field acidification with the tank on the with the acid tank on the tractor and dosing into the tanker directly. So there are a number of options for kind of recovering and maintaining nutrients in the slurry that will work in benefit of slurry nutrients, but at the same time reduce emissions. So that's everything from me, and I'll finish now because I think we're running over time. So thank you very much.
That's brilliant. Thank you very much, Dominika. And that's fantastic. You might stop sharing your screen. Thanks very much for all the information. So just to remind everybody again, there's a Q&A questions and answer tab on the bottom. We have a good few questions in there already, and I'm joined by Pat Murphy just to ask a few questions. I'll ask all of the other presenters to come back online again. Dominika, as you're there in front of me, just in terms of just ask you one question around. So for soils, the trying to shift pH takes quite a volume of material to do that. Is it similar in slurries or any kind of, small kind of packet of stuff that you can get that's going to do the job? Or is it really down to, physical bulk that you're going to need relatively large inputs to try and shift the quantities or shift the parameters that you want to shift?
In terms of reducing the slurry pH?
Yes.
I'm afraid it is bulk mostly because slurry has a large buffering capacity. So there's a few nutrients working there as buffers. So you need to add quite a lot of acidifying agent to drop that pH. So what you see is you might be adding acid, and the pH might be very stable and then drop more kind of more dramatically. So it might take more of the material, but it does depend on what material it is. With when we work with acidification with just kind of standard inorganic acids, they would be very highly concentrated. So in that case, you need small quantities. Obviously, when you scale up to a slurry tank, that's still not trivial. But that dosing is smaller. But when I showed the alternative acidifiers, such as maybe the grass silage effluent or apple pulp, those type of materials, those inclusion levels were kind of between 7 and 15%. So that's not trivial when you think about a slurry tank. So if you have a ton of slurry, you might need to add 100 kilograms or a liter of material. That's the 10% addition. So it really depends on material. That's why I kind of showed a caveat there of how practical some of those might be.
Okay. And just before we move on, so where do you think in terms of the widespread commerciality of this are we 2 years away, 5 years away? Are we still really in the learning curve?
Look, I would like to say, like, on some of those things, like, okay, so there's obviously commercially available additives there already, and I've shown there's, I didn't want to show names at the moment, but the paper is under the review, but there were a couple of materials that did reduce methane emissions, so that's already available on the market. The amendment that the University of Galway is working on, that's kind of pre-commercial, so they estimate approximately a couple of years before it might be available. It is a large body of work to get to the stage where it is usable, and and there's sufficient research to back it up. Okay,
so we're getting there.
I think we're getting there, but I would still be kind of cautious of of what exactly we're getting and what the label says.
Okay, very good. I want to bring Mark in there. Mark, there's a question in there around, you made a comment around bagged fertilizer or chemical P only lasting for the current year in comparison to organic phosphorus, which I think your comment was that it seems to be more resilient or seems to last a little bit longer. You might just expand a little bit on that.
Yeah, Patrick Forrestall has work going on looking at a range of organic manures, and I suppose the one thing, or sort of different organic source, but the one thing that's coming out of that work is that they seem to, what would I say, I suppose it's the organic P, that there's more resilience or longevity in terms of building soil fertility, where if you look at superphosphate, it sort of lasts the year. And I suppose, look, that's the way our advice has been driven, is that we apply a small amount of build up each year to build soil fertility. But look, I suppose it's just organic manures tend to be, I suppose, a better way of building, especially soil P levels. And I think it's the organic part that you're getting that drip feed of P over time, or as that organic part breaks down over time, you're getting that buffer or that supply of P.
Okay, thanks, Mark. Thomas, I might just bring you in. There's a question there around sodium and applying sodium with K, maybe to buffer the amount of K that's there. Certainly from a beet point of view, slightly different crop, obviously, but that used to be included in there in terms of the very high levels. Do you have any sort of comment around that in terms of that question?
Yeah, well, I suppose there's a few things. First of all, what was presented there was on ryegrass only swards. I suppose if we look at grass clover, for example, there's a tendency for other cations such as calcium, magnesium, and sodium to be slightly higher in the clover species as well. So maybe that ratio might be harder to bump up in terms of be more cations in the system already. Of course, you could go down the route of blend fertilizers with sodium and other cations in those as well. But really, in terms of avoiding tetany, one of the most practical things is just mineral licks, really, or maybe a magnesium nut or sodium nut, or if it's cattle out on an outblock, maybe a bucket lick or something like that, just to keep the other cations in the nutrition for them, really. So.
Okay. Veronica, I just want to bring you in there for a second. There's a couple of questions in there around people with higher Ps, I suppose, especially seems to be coming up, and people, I suppose, maybe a little bit worried about that they don't have a capacity to apply any phosphate at the moment.
Okay. So if you're in an index 4 scenario, you can't bring in chemical fertilizer, but you can still apply your own organic fertilizer onto the farm or onto the field in farm. But I suppose what we'd be saying is to try not to target those, because if they are in the index 4 scenario, then unless there's a case of lockup, the phosphorus in the soil is sufficient to feed whatever crop you're growing in it.
Okay, sufficient there. Pat, you had a number of questions there?
Yeah, and I suppose a longer one on that same point, and maybe to Mark. I suppose there's two reasons why you might not have a P allowance. One is that you're index 4, but the other is that you have a high level of use of concentrates. And if you're in the second category, what implications might that have for your allocation of slurry around the farm?
Yeah, I suppose, Pat, look, as Veronica is saying, you're targeting the slurry based on soil test results. I suppose one of the things that we are seeing, especially coming back from the signpost farms, is that the silage ground tends to be lower in K, where your grazing ground tends to be, lower in P's and K's, where your grazing grounds tends to be probably index 4 for P and K. So we'd be very much recommending people that you target the slurry back onto the silage ground, or use the soil test results as best as you can to target the slurry to the crops where you're going to see a return. Like Veronica had a good example there where she was showing, I think spring barley was an index 1, index 2. So again, if your silage ground on that farm is high for P and K, that Veronica showing it was, then the slurry is most recipient to the crop that has the biggest demand. Like, so yeah, look, it's very much trying to manage especially the slurry as best you can.
I suppose in that scenario, particularly if you are feeding meals at grass, the P from the meals are probably going out to grass as well. Anyway, question there: when you looked at reducing nitrous oxide emissions by 38% with appropriate pH, was that using a CAN or a protected urea?
That was using CAN plus sulfur, Pat. But I suppose the thing there is that lime is an easy win. Like, we can get the pH right at a very low cost, and when we get the pH up to that sort of between 6.5 and 6.8, let's call it, you actually switch off the denitrifying bacteria, and soils contribute about half of the emissions. Like, between soil and fertilizers, about 20%, and about half of those emissions come from soils. So again, you know what I mean? If we can get our pHs right, it's a big win for agriculture in terms of reducing our nitrous oxide emissions from soils.
Veronica mentioned establishing a cover crop post-harvest can capture excess N in the soil. Is this N at high risk of loss if establishing a winter crop after the cover crop?
So the use of short-term cover crops between the harvest and a winter cereal is becoming a lot more popular, especially in the risky soils. I'm based in the Midlands and around the Barrow, where our soils are very leaky, I suppose you'd call them, for nitrate. when it comes to the destruction of the cover crop afterwards, like the release of the nitrogen in that is going to be dependent on what's in the cover crop itself. So if it's got a low carbon nitrogen ratio, it tends to break down quite quickly. And if it's more fibrous material, it tends to break down quite slowly. Soil temperature also plays a role in that as well. But like the research, there was a research done in France, I think it was, that looked at the rate of the breakdown of these products, and it came down to that specific, and you know, the CN. And I would imagine a lot of the people who are using these short-term cover crops are using fast-growing crops like mustards, which are quite fibrous. So I wouldn't think that they would be a massive risk there myself, just because the soils are cold, they're wet, the material is probably going to be held until it starts to break down, and more in the springtime, which would be in line when the crop was going to use it most.
So, some prospect there for considerable benefit.
Yeah.
Pat, we have a question there. Just bring Thomas in there just for a second. Thomas, we've a very somebody with a really good memory. They're talking about, they were down at a walk down in Solihull, and they're saying that the what they've seen down there was the K levels were quite high. They were high index 4s, and I suppose they're curious around what parts of the farm were under that in the period of time that you were looking at it.
Yeah, so I suppose what I presented there would have been the mean soil test K, taking the average across all the paddocks in the farm over the course of the years. And we could see there in 2016 that the mean on the soil mean soil K fertility across the farm was 85 milligrams K per litre. So that's midway through index 2. Obviously, the spread of data around that, we'd have had some fields in index 3 and index 1, and averaging out in index 2. I suppose the overall goal from there was to increase that up across the farm over a number of years, just to get it up into optimum range of index 3 for your clover, really. So I suppose on a paddock per paddock basis, the majority of the farm got into index high index 3 or 4. I suppose then again, depending on where you put your slurry and where you harvest your silage, the rate of increase would be dependent on the management per paddock, really.
Sure, and look, these change over time, as was pointed out as well across that we can actually move those indexes up relatively quickly depending on the excesses that's there. I think you pointed out as well. One other question is there, Thomas, just in terms of the you made a comment here that somebody's inquiring about, where you said not one size fits all, and I suppose the question is around, is that as regards leaching, or is it uptake, or what is it?
Yeah, so I suppose part of my PhD is looking at that, you know, the current recommendations with our index system, that's fine and it's working, and, you know, general rule of thumb, 30 kilograms per hectare to get up an index. But I suppose that's not accounting for the nuances of soil type. There's obviously a big spread in terms of our soils across the country. So we're looking at it from that perspective, really. So we gathered soils from all over the country for a pot experiment, looking at how these application rates affect the change in soil test K over the years, and we found that cation exchange capacity of the soil is a good proxy for looking at how quick you can build up a soil in terms of its K fertility. So that's linked to your clay content predominantly, also your organic matter and that kind of thing, and your pH to an extent, but really it's cation exchange capacity. So where you're on low CEC soils, those would be the sandier, lighter textured soils, you can get up an index very, very quickly on those, because you're just boosting that plant available fraction, because there's no ability of these soils to hold on to K, really, you know, and release it to the crop over time. So you could apply 100 kilograms, for example, and boost your an index or two very fast on a light sandy soil. On the other hand, on a heavier soil, ones with maybe a clay content of over 22%, you're into higher cation exchange capacity there, and the ability of these soils to, I suppose, hold on to K as you apply it, and, you know, trickle feed it to the plant in subsequent years or seasons is much greater. So we're trying to tease that out at the moment, and maybe make a more soil specific recommendation list based on cation exchange capacity.
Okay, and obviously we have a huge amount of different soils around the country, and they will all certainly react differently.
Well, that's it. So I suppose if you could hone it into 3 categories or something like that, you know, that would make a more practical thing on farm level, you know. So
make it a bit easier. Okay, Dominika, just to bring you in there, there's a question there around. Obviously, you pointed to the fact that acids will reduce some of the emissions from the slurries, But on the other side of that, there's some alkaline type products getting back into the slurry. Will that then, on the other side of it, increase emissions?
It will, yes. Once the pH goes up, more ammonia will be volatilized. Yeah. So if you see, for example, like we actually did it a few years ago. One of the colleagues there added lime to slurry, and emissions increased dramatically. So yeah.
Okay, and I suppose similarly to the words Dominika here in the tillage world that I operate in, there's an awful lot of products coming to the market, various different types, whether they're biological or various other different things. Is there, you pointed out there's a number of commercial things that you're testing at the moment. How large is the capacity, or how difficult it is, I suppose, to try and test everything that's coming onto the market?
It's just not possible, Michael. And I suppose the question is, of the Teagasc role as well, like are we a body for testing commercial products? We're interested in research. We're trying to test as many as possible because there's so much interest from a variety of stakeholders. But at the same time, those products need to kind of fit in with the body of work we're doing. So it's impossible to test everything. Yeah.
Okay. Pat, do you have one or two last questions?
Again, for Dominika, just a comment on the potential of aeration.
Yeah, so look, aeration is also getting more popular now because of basically the health and safety and workability of the slurry. There's no need for agitation, so your slurry is ready to spread whenever you want to. And look, we use it here in Johnstown ourselves for those reasons. In the past, it's been shown to increase ammonia emissions. However, because you introduce oxygen into the slurry, aeration can reduce methane. So it is between the two gases. And it was the same with additives when I showed that, some additives work well on one gas, but not on the other. So aeration, kind of some of the new types of aerations with smaller bubbles, or maybe, not constant, but kind of just frequent aeration. The best case scenario is that it will reduce methane emissions without affecting ammonia. However, that kind of very vigorous continuous aeration, that's kind of in traditional sense, would have usually increased ammonia emissions.
Okay, and just a last final question. You talked about the suppression of losses and the fact that if slurry was intended for anaerobic digestions, it might reduce the losses. Is there any chance that the commercial value of that would pay for the cost of the product that goes into it?
I think it makes sense financially, yeah, because you're retaining so much more methane and carbon for the AD. I think it stacks up. And it is mostly that work is we're working on it in one of the collaborative projects, and the University of Galway is leading that work package, and it is looking well. And I should have mentioned as well what I showed, kind of the pre-commercial stage, and how it fits, how it's retrofitted into tanks. That's actually the research farm in Shannock there, where University of Galway have their presence. And they're seeing really nice results there.
Dominika, thank you very much. I think, look, we're a little bit over time. We're after running out of, there's more questions there that we would like to get around to, but look, we're just a little bit over time. So thanks very much for that. And indeed, thanks very much to Mark, Veronica and Thomas as well for their excellent presentations, and to Pat for helping out in the question time. In the background, we have a good few colleagues working away very hard, especially Yvonne Marr, trying to put all these bits and pieces together. So thanks very much to those as well. So listen, we've had I think a really excellent soil conference over the last 3 weeks, taken in bite-sized chunks so people could think about the bits and pieces that are coming up. Huge amount of technical material has come up along the time, but I think even more so, and there's an awful lot of very practical recommendations for farmers and industry indeed, that they can bring out to farmers on the ground in terms of timings when you can go out with various different slurries or fertilizers, that kind of thing. And that's combined with some of the other really excellent messages over the previous 2 weeks. So for all of those, you can listen back eventually to the videos to be put up online, and all of the presentations will be online on Teagasc within a day or so. So you can go back if you missed something or you want to have a look at it again. Excuse me, you can go back in and have a look at that. So look, with that, again, thanks very much for everyone who come online, and for all the presenters, not just today, but all the way through the last 2 weeks as well. Thanks very much for your input. And to Pat Murphy as well, who is the main organizer of these online conferences. And I think, Pat, you have a good few more conferences lined up over the next 6 months. So keep an eye out for those. There's obviously the conference, or there's obviously the signpost series on every Friday as well. So there's plenty of information coming at you all the time. So with that, thanks again, everybody. Certainly wishing everybody online a very successful year to come. God bless, and we'll chat to you soon.